Hello. So, my name is Noah Johnson, and I study physics with theoretical physics. And my presentation today is on what the pre-quantum model of atomic interactions can still teach us today. So, I wanted to start by looking at the timeline of development of atomic theory over time. So, we start off here, obviously very early, with very basic ideas of the atom, of just being a solid building block of matter, and then all the way up to the modern day models, which involve quantum mechanics. So we've got, thanks to the Schrödinger picture, the current atomic theory is based on probabilistic atomic wave functions. So this is the one we're used to. So throughout this presentation, I'll mostly be focusing on the very late development and sort of quantum onwards models of the atom and where those may have some shortcomings, and perhaps the classical models can actually be effectively used as well. So the rise of the quantum model of the atom came around in the 1920s when quantum theory completely revolutionized modern physics. So because of this, quantum mechanics was being applied everywhere in physics, and it was shown to be incredibly effective. And so because of this, a lot of the older classical models were then almost written off, and it was the prevailing theory that the quantum model was the correct one, because they were shown to be very accurate to experimental data, and so in a lot of cases the quantum mechanical model was deemed the superior, and therefore the classical model was written off. However, a really interesting paper came out in 1953 in which Gregory Vanier showed that in a lot of cases classical models can still be applied, and in some cases can even have advantages over the older classical models. So before we explain these places where the classical atomic models can be used, we need to quickly have a background on this phenomena called near threshold fragmentation. So what is near threshold fragmentation? It is a theory that effectively describes interactions where, after the interaction, three fragmenting particles escape, and their trajectories are chaotic and difficult to calculate. And during the interaction portion, um, they are interacting via inverse power laws, specifically. So it's also worth noting that in this type of interaction, the energy level of the actual potentials is roughly equivalent to the energy level of the system as a whole. And then these type of interactions come up in atomic and molecular physics. So saying that, we now want to look at some classical potentials in atomic systems. So in atomic systems, we have particles interacting via short, medium, and long-range potentials. And the classical mechanical approximations can be applied to medium and long-range power law potentials. So, of this form, where the potential is related to the interatomic particle separation R, and then you have n, which is some integer, and then beta is a constant. So this can be used to approximate any sort of interatomic potential that is medium or long range, by varying these parameters. And then the short range interactions can only be approximated by quantum models, so they are not relevant here. Key potentials of note is when you set n equal to 1, you have the Coulomb potential, as shown here on the left, and of course the harmonic oscillator potential when n is equal to minus 2 here, which is shown on the right. And these two potentials are of key importance for near threshold fragmentation type interactions. So, knowing this, when can we actually use these classical models for modeling atomic systems as opposed to using the quantum models? It can be shown that the condition to use a classical approximation where typically a quantum system would apply. This condition is that the time derivative of the de Broglie wavelength must be approximately constant in time. As that is to say, the de Broglie wavelength should be constant in time, so that its time derivative is roughly zero. And then applying this to our power law interactions, this sets a condition as such. And then in the case of setting n equal to 1 for our Coulomb potential, it gives the following condition, which can then be used to show that the classical approximation can be used for the Coulomb potential, where interatomic separation is asymptotically large, so r is approaching infinity, and therefore this will be satisfied, and then the Coulomb potential can be effectively modelled using the classical approximation. This can also be shown to apply to the harmonic oscillator in the case of weak binding energies. So what does this tell us? This tells us that the classical models and the quantum models will converge in the cases of large interatomic separation and weak binding energies. And it's known that these two conditions are satisfied in the case of near threshold interactions. So because the classical and quantum models converge and the classical approximation can be used, this shows that classical models still apply to this type of interaction and can be used to model these interactions. So this now leads us on to Vanier's theory of near threshold fragmentation, which was proposed in 1953 and is a purely classical theory. So despite the fact that quantum theory was significantly developed by this point, he based his theory on purely classical phenomena. It comprises of three phases of these interactions, where the particles enter via an entry channel and exit here via an exit channel, and the actual interaction is governed in what's called a compound state, in which they undergo these power law potentials, and they are in a chaotic and unpredictable state. So the key piece of understanding that was gleaned from his theory was that he discovered there was no deterministic path for these particle trajectories after they exit the compound state. So it was shown that using the quantum mechanical approach, the expectation values for trajectories could not be effectively calculated, and this classical approach therefore tells us why this is the case. The applications of this theory are widespread, so things like atomic and particle physics. His theory was shown to predict the behavior in these chaotic and unpredictable systems, and it also can be applied to celestial mechanics, so where you have chaotic dynamics occurring with things like gravitational interactions. And not only this, but in a wider sense, it reinforces that classical theories can still apply in a lot of modern physics. It's also worth noting that the classical models for these near-threshold interactions are computationally much easier and less demanding to simulate. So this graph here is showing experimental data with the blue dots, and then the dotted line is the quantum prediction, and this thick line is the classical prediction. So it's showing that the classical prediction much more accurately fits with the experimental data. So this is a great case for using these classical approximations over the quantum model in certain situations. So the key takeaways from this is that classical physics can still be useful even despite the invention of quantum mechanics, and there's a lot of situations where classical mechanics actually outperforms and better models certain interactions. And Vanier's paper showed that it was especially useful in these near threshold interactions where there's chaotic interactions involved. Thank you very much.